Hello and welcome to this video on rotational motion. Specifically today we're going to be talking about centripetal acceleration and the total velocity of something in a rotating system. The easiest example of what I'm talking about with the total velocity is a car. When you're in a car, let's say you're driving down the road at 60 miles per hour, your velocity, the translational velocity of the car, is this way. You're heading down the road in that direction. And the tires are also all heading in that direction. So every point in the tire as a whole has that velocity. So I can just copy this vector. And they're all heading that way. That is your translational velocity. The problem comes with the tires. The tires aren't just moving forward, they're rotating, they're spinning. They have a rotational velocity. The car tires are moving like so. And the points on the tires will make these circles. Because of this, the total velocity of the car tires, like at any given point, is the sum of these two vectors, which means that you get vector addition. Now, we can talk about each of these points individually. Well, let's start with the one on the bottom. The car as a whole is moving 60 miles per hour, which, as we've said previously, is 26.82 meters per second. That is the total net motion of the car. But how fast is the tire moving? Well, the tire is also going to be rotating. It has to be rotating in such a way to give you that 26.82 meters per second, which means that the velocity of the tire, the VT of the tire, is going to be the 26.82 as well, which means that the car tire at the bottom is effectively standing still because of how the rotation works. That point is not moving. And this actually explains how car tires work. Because that tire is standing still, it's a fixed point. It's going to use that frictional force to push against the pavement and push you forward. That is why when we talk about cars rolling to a stop or car tires moving, we use mu static max as opposed to mu kinetic. Because while the tires are moving, the point at the bottom, first of all, isn't, and secondly, the point of contact isn't. It's a fixed static motion, and it's the rest of the tire that's rotating around that point. Relatedly, that tells me that my total on the top end is going to be double that, or 53.64 meters per second. But what about this one? What about this side here? What would the velocity of a flea right here be? Go ahead, give it a try. Check back after you're done. Okay, let's take this from the top. I first redrew the diagram to get a better representation of what the vectors actually looked like, so we can see that the two sides are equal, which gives us a triangle that's a 45, 45, 90. I could do a squared plus b squared equals c squared in tangent, but looking back at my geometry, my trigonometry, I can go, okay, the two sides are equal, so that has to be a 45-degree angle here. The hypotenuse would be one of the sides times the square root of 2. Either way gets you there. But what about the centripetal acceleration experienced by an object? Well, it might be tempting to say that the acceleration on the object at the bottom is 0, or increasing here, or varying as it goes around. But acceleration depends on the tangential velocity.
Further,
The angular velocity is still the same, so the angular acceleration should be the same. The acceleration of the object will remain constant, or the centripetal acceleration of the object will remain constant, because it's not speeding up or slowing down.
provided there's no angular acceleration. A quick example of calculating centripetal acceleration.
On the screen we have a picture of a centrifuge. It's used to spin and separate blood into parts. If it spins at 11,500 RPM, and the ends are 8.75 from center rotation, what's the linear speed at the end of the tubes, and what's the centripetal acceleration at the end of the tube? Go ahead, calculate it, check back after you're done. Okay, if you've done your calculations carefully, you should look like this. First thing I did was calculate my
Angular velocity.
at 1150 pi radians per over 3 radians per. I got 1150 pi over 3 radians per second. Works out to a decimal, but ultimately not too relevant. Calculating the speed at the edge of it is 150.37 meters per second. Calculating the acceleration gives you 126,899.81 meters per second squared. Anyways, thanks for watching. Have a good one.